So let's talk about Ampere's law. Oops. Okay, to talk about Ampere's law, it's a little tricky. Okay, I'll be honest. It's a little tricky because with Gauss's law, we started talking about flux. And when we talk about flux, we looked at a positive charge or a negative charge being like this source or sink of like electric field flow. Like these field lines would pour out of positive charges, or they would pour into negative charges. They would, to a certain degree, you can think of them as being created or destroyed, kind of like that. I mean, they're not created or destroyed, but you can visualize it that way. So you can kind of visualize it flowing through your Gaussian surface, right? Actually going through. With magnetic fields, though, they don't actually get created anywhere, right? And they don't actually go into anything either. They go in a loop. So to understand Ampere's law, actually, what we should do is look at Gauss's law for magnetic fields. So let's look at Gauss's law for electric fields. Whoops. Okay. When you look at Gauss's law for an electric field, you'd have a positive charge, you do this Gaussian surface, and you look at the flux, right, of the electric field emanating from your positive charge, right? And at your surface, there would be some area vector representing that piece, that spot where you're getting electric field going through that area, right? So we said that there's a little bit of flux at that spot. Okay, and then we would add it all up. Okay, we would add it all up. We add it at every spot. So the area determined, or the differential area that we're looking at would determine what the electric field is at that area. And then we would add it up over all the area. And if we chose a closed surface, okay, specifically if it was a closed surface, we would find that in the end, it didn't matter the shape, the total flux through any closed surface would be directly related to how much charge is on the inside divided by epsilon naught. And it's important to think about why the shape didn't matter. If you started going further away, right, if you had an odd shape, like a potato, okay, and you have electric field going further out, although it would spread itself out more than when you're close in. See how it's kind of more concentrated as you get closer, and it spreads out as you get further. But as it spreads out as you get further, you have more surface area to look at, right? Because it expands out. And it turns out that the surface area increases as you go further away at a quadratic rate, and the electric field spreads itself thin at an inverse square rate, and that it would cancel itself out. So that it didn't actually matter if you went further away or you came closer, because as you went further away, you had that reasoning, right? It would spread out, but you have more of it, and so on and so forth. We also looked at how do you look at flux for a charge outside your Gaussian surface. The flux from any charge outside your Gaussian surface added no net flux, because any field lines going in would eventually go back out, right? And so on and so forth. So how does that look then when you look at Gauss's law for magnetism? Okay, let's think about that for a second. When we look at a current carrying wire. Right? And whatever kind of closed surface that we try and make, the magnetic field created by this wire is going to look something like this. Right? It's a loop. And maybe really hard to visualize because we're trying to do this in 3 dimensions. But what do you think if I added up all the magnetic field trying to exit, okay, trying to exit my Gaussian surface? What would that add up to? How much flux do I have here if you think about flux in terms of magnetic field only leaving the surface? Right, it goes in and it goes out because the magnetic field always goes in a loop. So no matter where you look, wherever it goes out, it must end up coming back in. Or, if anything, at best, what it can do is it can go parallel to the surface, right? It can go parallel to the surface, but even then, if it's parallel to the surface, then it's not going out or in either, right? So either it goes out and it comes back in, or it stays parallel and goes neither out nor in. So actually, this is Gauss's law for magnetism, and is that the net flux around any closed surface is actually equal to 0. Okay, there's a couple implications of this. This says that, again, you have no magnetic field, no magnetic flux out or in, but also this means that there are no monopoles. That is kind of the implication of Gauss's law for magnetism. There are no monopoles. There's no way where you can have only magnetic field coming out. It always comes back in. Yeah.
So just looking at the diagram, shouldn't the arrows be pointing the opposite direction?
Oh yeah, you're right. You were correct. Whoops. Yeah. It is going to the back of the page. Is that? Yeah. Yep. Right.
When you're saying like charge goes out, always goes back in.
The field.
Oh, the field. You're talking about like this.
In this one, yeah. The magnetic field here, B, created by this current carrying wire, I. If you have this kind of any kind of Gaussian surface you want, right? If you zoom in on the surface, if it comes out at all, at somewhere else, it's going to come back in. Yeah, it has to. Okay. Okay. So, what I'm going to describe here is then there is. So instead of looking at how much the field is leaving or entering, what we're kind of looking for is a way to relate how the magnetic field goes in a loop, right? And how does that relate to the current on the inside? And that's what Ampere's law does. In calc, okay, there is a way of representing how much a vector field tends to turn. And it's called the curl. And I kind of show you what it looks like. This is something that you would see in Calc 3 in vector calculus, but I'll just introduce it to you, okay? Curl of a vector. It's kind of neat. And I think it's worth looking at, okay? So I'll just write it out, but it looks like this. This is a symbol, the gradient symbol. And what it is if you were to do this as a vector, okay, what would the vector of this gradient vector look like? You guys remember matrix notation a little bit? It would be like this. I'm trying to stretch your calc muscles a little bit. What does that imply to you? The slope, right? Yeah, in each direction. So this is kind of like looking at how does something change in the I direction, right? So is it expanding in that direction or is it contracting in that direction? But it's a cross product. It's a cross product with your magnetic field in the X and your magnetic field in the Y and your magnetic field in the Z. So, in other words, this magnetic field, if you're in one spot, okay, try and diagram. Let's say in this spot the magnetic field is this way, and I change position, some different position changed in position X, right? And now my magnetic field is this way. My magnetic field, when I changed position X, changed magnetic field Y. So it turned. So, in other words, my position change vector has a perpendicular component to my magnetic field change vector. So there's this cross product. That cross product is perpendicular to both, downward. Does that make sense? My position change is like here, and my magnetic field change is here, and so there's this twisting effect. Okay? This is This is mathematically how you describe how a vector field is turning. Okay? And this is what we call a curl. So you might talk about the curl of, in this case, a magnetic field. Okay? And that represents, right, if you look at the magnetic field wrapping around the wire, it's turning. Okay, it's turning. In fluid dynamics, you use curls to describe vorticity. Okay, in other words, how does air turn? And is actually used a lot in aerodynamics because essentially there's this theorem, or this math representation that the only way you actually ever have lift is when you have circulation. And I don't know, there's a lot of math that goes into it, but it's kind of the same idea. When you have this kind of circulation of air, you have air going faster on top than on the bottom, then there's this net kind of motion of air that is kind of like in a circle, and then you create lift. Okay, so we don't have to do the math of this. What I'm just trying to say is that there is a mathematical representation of how this magnetic field is turning. If you look it up, it's kind of interesting. Yeah.
So how do you multiply those matrices?
Yeah, so you will learn that when you get to vector calculus. It's actually not that complicated, but it looks kind of weird. The way I learned it would be you go like this, and you do the first one on top. Oops, there's nothing here. D, D, Z. Okay, if you're interested, this is how you would do it. And so you kind of put it together like this, and it's kind of weird, but you have an I term, and the magnitude of the I term is this determinant. It would be, yeah, d dy bz minus d dz by in the I direction. And then you add the j direction, which would be this, and then you do the determinant here. That's just mathematically how you would compute it. Okay, I think you would have to. I don't remember the theory as to why that works out, but basically, if you look at it this way, your cross product should not contain anything in the direction of it. It should be perpendicular to both, right? So I is perpendicular to y and z, so it has no x components. in that cross product. And then so on and so forth. You're looking at the product of the perpendicular pieces. And so you can keep going. So this would be like d dx of bz minus d dz of bx in the j direction, and then you add the z direction, or the k direction, I guess. Yeah, you can actually calculate it out. Whoops,
So
I guess.
it's not just going to be AB cosine theta or sine theta.
No. If you want to keep it as a vector representation. So I guess I'll put it this way. This is a very generalized way of representing it. When we did it in class last time, and we said like let's say the force, right, would be QV cross B, right? Most of any problem that you'll see on this AP exam, you will have two vectors in a plane where your cross product is going to be only in one direction, only in like the z. I'll put it this way: we were able to say something like this: QVB sine theta, right? Something like this, and we said like here's like V, and then maybe here's B, and here's some angle, and then F would be perpendicular to that. What this gives you is only the magnitude, and the direction we're saying is outside the page. And we could have a coordinate system that was maybe like here's the x direction, here's the y direction, and then this would be like the z direction. What this is saying is, what if you had V that had all three components, right? You have your Cartesian coordinate system. I'm kind of running out of space, but if you had a Cartesian coordinate system and V was like going this way, right? And what if like B was going like this way, right? Then your magnetic field would be like pointing backwards in some odd direction with all ijk components. To do that, you have to do all this crazy business if you want to keep into account every component.
Why don't you just reorient the axes?
Well, you can't, because if, let's say you have three particles going on, right? And you want to have the relative directions of everything. You can't each have their own components or their own coordinate systems, right? If you want to talk about everything moving in one common coordinate system, I mean, it could be all over the place. So mathematically, that's how you work it out. In any case, let's go back. Okay, so the math is kind of, well, I think it's interesting. I was actually talking with Mr. Grassman and Mr. Buck about Calc AB and Calc BC and kind of the combination of the calc that we do in here and the calc that they do in there. And we're talking about like how we can combine some of the things we discuss. I heard that in Calc BC you guys were doing a little bit of vector calculus. So this kind of falls under that a little bit. There's another version of this. If the curl describes how a vector field turns, there's another one called the divergence, which is the dot product. It describes how a vector field expands or contracts. It's kind of neat. Okay, well, why do I talk about the curl of a vector? Well, there's a theorem that describes how the curl of a vector is related to something called a line integral. Okay, so I'm going to introduce something here. You guys heard of line integrals before? Okay, I hope you have your attention now. So, when we talk about flux, flux was the flow of a vector through an area, right? And we talk about how you'd have to use a surface integral to add up all the area on that surface. A line integral is a measure of the vectors along a line that is parallel to the line, okay? And so you can kind of see why that's very useful when we talk about current. Okay, so instead of essentially when you use Gauss's law, you use a surface. It's kind of weird to use a surface around a line, a current. So instead, what we do is here's my current again. Okay, and what I'm going to do is I'm going to draw a circle. That is my Amperian loop. Okay, so just as you have a Gaussian surface, this is an Amperian loop. It is an imaginary fictitious loop, a mathematical loop. Okay, and it could be any shape, but for now we're just going to use a circle centered on the wire. Okay, and what we're interested in is in a little segment of wire, right? What is the dot product of the magnetic field with that little bit of arc we'll call ds? ds has a certain direction. In this moment, it might be pointing like this. Kind of like with Gaussian surfaces, there's a distinct outside and inside. In an Amperian loop, it's not as distinct. You can have your Amperian loop, with ds in one direction or the other direction. I don't think there is a real particular way to do it. Okay, something you should know about Amperian loops. Okay, it's very much in parallel with Gaussian surfaces. You're looking for symmetry, as much symmetry as you can get. See, because the magnetic field created by this wire is going to go something like this, right? It's looping around. And when we add up this value, this dot product, okay, the dot product here is how much the magnetic field is in line with that segment at that moment, right? How much is that magnetic field in line with that that little segment? And then we add it all up, okay? And not only do we add it all up, but we want to add it up in a closed loop, okay? Then we're looking for this line integral. Okay, the line integral is looking for how this field vector is following that line, essentially. The same way our surface integral, our flux. Guys, the same way we're looking for how the electric flux is perpendicular to the surfaces. Okay. Okay, let's try and do this then for this circle. Okay, if it's specifically a circle, it's going to have a certain radius r. Okay, so how do we actually calculate this? It's not flux, okay, but it is this line integral. Okay, we already know that for the magnetic field around the wire, it's this. All we have to do is show that everywhere along this circle, the magnetic field is parallel to S and is constant. Just like Gauss's law, right? In Gauss's law, when we actually tried to solve the integral, we didn't have to do any actual calculus. We did a lot of simplifying steps to show that the field was constant everywhere. So essentially, we're using the same arguments here. Due to symmetry and shape, this becomes this. You lose the dot product because everywhere the magnetic field is going to be parallel to that circle, as long as this circle is perpendicular to the wire, right? You know what I mean? But the plane, if this plane of the circle should be perpendicular to the wire. You can't have a slanted circle. It wouldn't work. But if it's straight up and down, then it's all going to be in the direction of ds. And because of the nature of the magnetic field created by a wire, it's constant everywhere on that circle. Okay, so then we get this. Mu naught I over 2 pi r is the magnetic field. ds, what would be the integral of ds? Okay, how do we relate that to r? It is s. It'd be the total s. The total s of this circle. 2 pi r. Nailed it. Oh, snap. So, following from all the analysis that we did with Gauss's law, what do you imagine that Ampere's law will look like? Some line integral will be directly related to the current on the inside. This is Ampere's law. And similarly, what it's saying is if you take a complete closed path, actually, it doesn't matter what the shape is of that closed path. It could be a square, it could be a rectangle, it could be amoeba shaped, whatever, right? If you add it all up, then it will be directly related to the current flowing through the cross-sectional, the area of that loop. Okay? Okay. Okay, yeah.
Does radius have to be constant for like Ampere's law to apply?
No. So we can extend Ampere's law to say more generally. Actually, here, let me see if the book has a good diagram. I think it does. This gets into the realm of things that are hard to draw. So,
And does it apply to the current that's going through the wire, or like?
it is the current going through that cross-sectional area,
Okay.
and then so here's the thing. When you're trying to decide what the loop is, that loop, because it's a closed loop, is tied to the area that would fill in that loop. So you can either say that you have a loop and then there's an area inside of it, or the loop is the boundary of the area that you're using where you have current going through that area.
So if R was there in the wire, then there would actually be R in your equation for.
No, see, because if you, it's the same thing as Gauss's law. When we talk about Gauss's law, we said that the further away you get a weaker field at an inverse square rate, but you get more area at a quadratic rate, and so they cancel out. It's the same thing here. See, as you get further away, your magnetic field gets weaker at an inverse rate, but you get more loop at a linear rate, and they also cancel out. So actually, the size of the loop in the end doesn't matter. And because of the nature of the dot product, the shape of it doesn't matter either, because the only pieces that matter are the pieces that are turning and not expanding out or in. So even if you have a loop that looks like this, okay, the integration path is a closed curve. You can encompass any number of currents, but what it's saying is that the net magnetic field, or the sum of all the magnetic fields on that loop, are directly related to the net current penetrating that loop. And that is Ampere's law. So the usefulness of Ampere's law is just like Gauss's law. You can't use it if you, or it's not that you can't use it. It's honestly not that helpful if you have some crazy shape. Most of the time, you're looking for something with a high amount of symmetry so that you can go from here to here. You have to be able to, at this level, okay, you have to be able to reasonably establish that the magnetic field is constant everywhere on your loop, and then that it's everywhere parallel to your loop. Or you can do something where you chop it up. Like the cylinder, when we did Gauss's law for a cylinder, we would ignore the ends when it was in a wire because there was no flux through the ends. You'll see that we do that sometimes too. We start with a closed loop, but there may be sections of the loop where there's no magnetic field at all, and it doesn't matter. And so we break it down into certain interesting parts. We'll see that with solenoids too. Anyway, so you can have any shape you want. It doesn't matter. Okay, what you end up getting is that sometimes, right, we know that the magnetic field created by a wire expands out in a circle, or not expands out in a circle, but is constant on a circle, and then it gets weaker as you go further out. So at some points, when your loop is going away from the wire, the magnetic field may not necessarily be, I try my best to diagram the magnetic field at a certain point. The magnetic field may not necessarily be parallel to S, right? Only the parts where it's parallel to S do you actually count it, but then those are further away, some are closer in, and the net effect is that you're essentially just adding up all the parts that actually, loop around. And yeah, it's kind of hard to diagram because it's not just one circle; it's multiple circles, right? This magnetic field is created all over. As you just get further out, it gets weaker. As you get closer in, it gets stronger, and so on and so forth. As you get further out, you get more Amperian loop. As you get closer in, you get less Amperian loop, and the combined effect. The combined effect of it getting weaker as you go further out and having more Amperian loop as you go further out cancel out. Yeah.
So I guess my question is, like, if your wire is thick enough that you have your Amperian loop within the wire, does that make it like variable with R then?
Yes. Yes. Kind of like when we did the amount of electric field from a charged rod. Yeah. So this is how. Well, I'll put it this way. So we had when we did electricity and when we did electrostatics, we had this, right? And that you could use this for a distribution of charge to figure out the net electric field from any distribution of charge, right? And we saw that when you integrated this, sometimes it was really messy and cumbersome. And so then we used Gauss's law to say, well, if you have a high amount of symmetry, you can simplify it. And then it just becomes a matter of shape. If you have convenient shapes, you can calculate this very easily. Very similarly, for magnetic fields, you can do the same thing. QV cross R, whoops, this is that. And then you could turn it into a differential piece of a wire. So this is like a singular charge, right? Moving, you get magnetic field created by it. If you have some length of wire of whatever shape, you can do something similar. Right? So that instead of looking at one particular charge, you can transitioning into a distribution. So this is a distribution of current. And you can add it all up, and you can do it in a loop, you can do it in a straight wire, whatever, right? But again, we said that when you integrate this, this can get messy. So if there's a high amount of symmetry, then now we do a line integral instead of a surface integral. This is looking at adding up all the flux through a surface. This is looking at all the magnetic field along a line as related to the current going through it. Okay, so this is Gauss's law. This is Ampere's law. Sorry, if you want to get, there's this accent there. I don't know how that works. Yeah.
How do you distinguish between a surface integral and a lattice?
Well, technically, if it was a surface integral, it would be there'd be two integral symbols on top of each other. Yeah. Yeah.
And what does the D stand for in the magnetic field wire? Is that just the length of the wire?
No, so D in this one is your distance away from the wire. Yeah.
So it's R.
Yeah, it's essentially like R. Yeah. Okay, so take a look at this example, right? Pretty much exactly as Morgan was asking about. How do you figure out the magnetic field inside of a wire? This is on page 937, a very good example, one definitely you ought to know. Good example on page 937. Okay, that's a good one to look at. So, how do you figure out? You have a wire of radius r carries a current I. Find the magnetic field inside the wire at a distance r less than big R on the axis. Okay, so one of the assumptions that we'll make is that the current density is uniform across the cross-sectional area. So in other words, it's not like you have more current flowing through the center than along the outside or anything like that. That's important. So you can see that the wire has cylindrical symmetry with all the charges moving parallel to the wire. That current is going to create a magnetic field that goes like this, everywhere. What this also shows with Ampere's law is that the magnetic field around the wire, or not around wire, in that Amperian loop is only due to current going through the loop. Okay, any current going outside of the loop will not create any net curl or rotation or magnetic field along that loop. Okay, so, well, one thing you can see is that the result is it grows linearly. Okay, again, you can go in and you can do all the math. Take a look at, very similar to Gauss's law, actually. I think we should visit this. Most of you guys, folks, had trouble with Gauss's law in figuring how to figure out how much charge is enclosed. Okay, looking at all the tests, if you figured out how much charge is enclosed, you got the answer right. If you couldn't figure out how much charge was enclosed, you got the answer wrong, and you would lose lots of points. So you need to look at how they are, this whole uniform density thing. You got to figure it out. So how do you figure out how much current is going through this loop of radius little r? Well, you have a total current of big I going through the whole thing, right? And that is your, so if you have a total current I going through the full surface area, pi r squared, that is your current density, J. If it is uniform current density, this should be the same as the, did they use the little I? Oh, they called it I through. Okay. Then that should have the same ratio as the current going through your Amperian loop divided by the cross-sectional area of that Amperian loop, or the area enclosed by that cross-sectional loop. This, how to use current density, you guys got to figure out, because that seems to be something that you guys get stuck on a lot. Does that make sense why this works?
Why are you dividing by wire?
Because I'm looking at two ratios. This is the ratio of the full wire. This is the ratio of the intersection of wire that I'm looking at specifically. Yeah. So it's comparing this to the full. Okay, so then when you solve for I through, It's ends up essentially just being a ratio of the square of the radii. But don't memorize this one. Figure out how to figure out this one. This is important. Once you know this, right, this is all trying to deal with the right-hand side of Ampere's law. Like Gauss's law, there's a left-hand side, right-hand side. Same thing with Ampere's law. You kind of do them separately first. So here's the right-hand side is solved for. Okay, and then we take care of the left-hand side. Right? And again, you're generally looking for shape and symmetry, yada yada. Right? We know from symmetry of the wire that B is everywhere tangent to the circle and has the same magnitude at all points in the circle. Therefore, this line integral can turn into just a product. And then you solve for I. Or sorry, you're solving for B. Okay, you're solving for B. So, inside the wire, it grows linearly. Outside the wire, it decreases inversely. Yep.
Can you go back?
Yep.
Is that BL?
Yeah, so they used L as the, instead of using S, they used L to represent the full length of your Amperian loop. L is the length of your Amperian loop. It would be the integral of the ds all around. Yep.
What's the difference between I and I?
So this Amperian loop is we're trying to figure out what is the magnetic field at this distance away from the center, right? Some distance little r. And so there's a certain amount of current only going through that loop. That is not the full current, right? Because there's some charges going through the outside of that little loop, and there's some charges that are going through the inside of that loop. So I through is the current only going through your Amperian loop. And then big I is the total current of the full wire. Yep.
I don't get how they got the equation for B.
This one?
Yeah.
What about it?
Like the equation before it.
This one?
So I understand like where they got. So like if you look at the equation for B of wire, it's mu naught over 2 pi times I over D. Why do we not need to use the D? I'm having trouble explaining.
You mean why aren't we using this one?
Yeah. What equation are we using to solve to like get our integral B?
We're not actually using, we're solving for B. We're not actually substituting anything in for B.
Okay.
So what we're doing is this is the left-hand side of Ampere's law, and we're simplifying it, making assumptions. So there's no actual substitution here. What this is just, we're saying that B is constant everywhere on the loop, pull it out of the integral, and then the integral of ds is just the length of the loop. And then we're solving algebraically for B. Yeah. So we're not using that method. This was solved for using an integral of this, which is different. That's like the brute force method, the hard method.
Looks like they did
Yeah.
substitute one.
Say again?
It looks like they did substitute one. It says BL is equal to 2 pi RB above that, and then it was like
No, they substituted for L. That's not a substitution.
no, there's never mind, that's L.
L is 2 pi r.
I don't think I can jump to this is just a cross section.
From here to here?
No.
From here to here?
Yeah, so like, why can't we just replace 2 pi RB with like what's on the right side?
So the L is the length of the Amperian loop.
Yes, I understand that.
So that's 2 pi r.
I get that too.
Yeah.
I just don't get the B.
The B is what we're solving for. B was always there. It was here, and what we did was because of the shape. So I guess what the step they're skipping is they're doing this. Actually, yeah. So what they're saying is that this line integral b ds is equal to b integral ds. So there's no mathematical substitution going on here. This is purely from the shape of my Amperian loop. Then what is the integral of ds? That's 2 pi r. So this is 2 pi r. This is the left-hand side of Ampere's law. So we're setting the left-hand side equal to the right-hand side.
I didn't understand where they got the right side.
Ah, yeah. So that's the thing. It's like you're approaching it from two sides, and then you bring them together, and then you solve for b. Yeah. So the right-hand side, that was all from figuring out how much current is going through,
Yeah.
and then that's that. And then this is like the left-hand side. Yeah. Okay. Cool. Any questions on that? Yeah. Little r is right there. So everything out front here is a constant. That's what makes it linear. As a good exercise, you should be able to use Ampere's law to get this again. This is for outside the wire. And you should be able to do Ampere's law to get that. This was doing Ampere's law to get the magnetic field inside a wire. You should be able to do it for outside a wire. Okay, questions on Ampere's law? Okay. Yes. That's all right. Okay, so fundamentally, right, Gauss's law was not a new law of nature. It is an analysis of Coulomb's law, right? Same thing with Ampere's law. It's not a new analysis of nature. It's from the Biot-Savart law. But it's a little different because actually, we'll see later, Ampere's law is a little more complex than what the Biot-Savart law shows. The Biot-Savart law, we'll find, is actually incomplete. And so when it comes to magnetism, you'll actually see Ampere's law be the explanation for the nature of the creation of magnetic fields. What it's saying is, this is also saying that the movement of charge creates a magnetic field, right? It's the same thing. But there's actually one more piece that Maxwell adds to it later that makes it a more complete explanation of nature than the Biot-Savart law. So actually, you won't hear about Biot-Savart law as much as you'll hear about Ampere's law, even though when you talk about electrostatics, Coulomb's law is the more fundamental explanation. We'll get to that a little later. Okay, so we can finally get to solenoids. So we talked about a solenoid a little bit. A solenoid is you take a bunch of rings and you just put them together. Okay, it's my slinky. Slinky is essentially a solenoid. And when you put them all together, it is interesting to look at how you use Ampere's law to figure out the magnetic field inside a solenoid. So let's take a look. You got current going in and out, and then in and out, in and out, in and out. And it's like you're taking the slinky set, okay, and you're chopping it like this, right? You're chopping like this. Okay, so the magnetic field created around from the top goes around like this. It goes this way, underneath, and then to the left above. But you can kind of see what they were trying to show here is that as you add up a whole bunch of loops, they add up in the center, but they actually start to cancel out on the outside of your loop. On the outside of your solenoid, they start to cancel out, right? Because this, the current going into the page on the bottom creates a magnetic field to the right everywhere above it. But this current coming out of the page creates a magnetic field in the same direction below it, but in the opposite direction above it. And so some of it cancels out. So in an ideal solenoid, what you get is that there's no magnetic field outside and only magnetic field inside. Okay, that is an ideal solenoid. Just like an ideal capacitor has electric field inside and no electric field outside. The idea is that they cancel out outside and add up on the inside. So take a second to make sure that that makes sense. Yeah.
So why does the magnetic field that's going in like this direction on the outside get completely canceled out?
It's because if you have a whole bunch of these wires, the idea is your
inside would be going this way,
uh-huh,
and the outside would all be pushing this way.
in the opposite direction. Yeah.
And there'd be nothing to cancel it when it's going in the opposite direction.
They are canceling out when they go in the opposite direction. Because you add them up like vectors, right? So it's kind of weird because you really have to think about it like if it is an ideal solenoid, it's like an infinite set of these, right? Just like with a plate, an infinite plane of charge. If it is everywhere, the distance away from the plate loses its meaning, right? So this is like for a line of charge, but imagine you have just lines of charge all lined up. The distance away kind of loses its meaning. You can't tell the difference between whether you're far away from the line or close to the line if they're all lines, if it's just like a whole series of lines all stacked next to each other. So that if your distance away kind of loses its meaning or effect, then all that matters is that the top set of wires creates a magnetic field outside of it in one direction, and the bottom set of wires creates a magnetic field in the other direction, and then they'll cancel out. But inside the loop, they both point in the same direction, and so you only have magnetic field there. You'll have to kind of do your right-hand rule, convince yourself, but they cancel out on the outside. Okay, so what does this mean? So when you do Ampere's law, I want you guys to look at the way they do Ampere's law here, because it's really weird. Okay? Look very closely. The loop doesn't encompass both. It only encompasses a certain set of wires. In this loop, there's only one side that actually has any magnetic field parallel to ds. And that is the bottom side. Do you guys see how they're doing this? Here, the magnetic field is perpendicular to ds, because ds goes up and down. So when you look at BDS, it's 0 on the sides, right? So kind of like when we were doing the Gaussian, the electric flux through a cylinder in a line of charge, we said there was no flux through the ends, and we just like threw them away. It's kind of the same thing. There's no magnetic field parallel to these, and there's no magnetic field on the top. So it's only the bottom side that actually matters. Okay? So if we choose a certain length L, that length of L is going to have some number of loops fit inside that's going to have some number of current, like repetitions of current going through that loop. And then on the left-hand side, it ends up just being B times L. It's just actually L. Not even 2 pi r, none of that. It's just L. So this is important. What we find then is that this, you need to know this. I'm not sure this shows up on the equation sheet. Oh, it does. Okay. When it says B sub S, that is the magnetic field from a solenoid. Notice that is now little n. The little n is the number of loops per length. It's like your loop density. Okay, number of turns per unit length. In other words, it's like a concentration of loops. So the more concentrated your loops are, the stronger your magnetic field can be. And then the stronger your current is, the stronger your magnetic field can be. Okay, so if I take my solenoid and I spread it out, right, it will weaken my magnetic field. This is very possibly one of those kinds of questions on the Fourier response where they'll say, here's a solenoid, derive this. So you need to know how to derive this from Ampere's law. So, in other words, study page 939. Yeah.
It's on a test. Say that was the question that they gave on the AP exam. If you just wrote down the section that's integral, closed integral of b ds, and just wrote that section down,
This part?
you would get 4 points.
If you wrote this, just the
entire section, all 3 lines.
all 3 lines, you would have to add something in the diagram to indicate that this line integral turns into BL. You have to explain this. You can't just go from here to here without explaining that only this part, the bottom part, matters. Okay, so to a certain degree, it's not an equation thing, it's like an explanation thing. But if you can get that left-hand side, the right-hand side is pretty straightforward as to why that's the number of loops, the amount of current going through. And then, yeah, that will work. This is essentially the derivation of this. Yeah. So the main idea here is that in an ideal solenoid, the magnetic field is constant everywhere inside the solenoid, not just in the center. Okay, if you have one loop, we had an equation that gave us the magnetic field in the center of that loop. But if you have a whole bunch of loops, right, an infinite line of loops, then it becomes a matter of the concentration of the loops. And it's the same everywhere. Now, obviously, if I take this and I stretch it out like this far, then you can't really represent this as an ideal solenoid, and it breaks down, right? Because they're so spread out that you're not going to have a uniform magnetic field everywhere on the inside of the loops. But if they're really, really close together, you can kind of model it that way. That the magnetic field towards the top is the same as the magnetic field towards the bottom, left, right, everywhere. Okay, we're getting there. There's still a little bit left in chapter 32. Homework is up on Mastering Physics. I also put extra problems for practice, but please do not put this off, you guys. It's not good. Please do not put this off.